Here we're going to find the equation of the surface generated by letting the curve z equals y squared revolve about the y-axis. So I'm going to draw a rudimentary picture of what's going on in the yz plane, and then we'll proceed from there. Alright, so here z is the dependent variable. It depends on the value of y. I think it's generally best to put the independent variable on the horizontal axis and the dependent variable on the vertical axis. Okay, so in this case, the graph is going to be a parabola, and it's going to revolve this way. Alright, so what we need is this distance, the distance from the axis of revolution to the curve. That's going to be the radius of a circle that is generated by letting this point revolve about the y-axis. Right, so that point is going to revolve about the y-axis and generate a circle. So r is going to be that z value minus that z value. Well, that z is determined by the curve z equals y squared. And that z value is going to be 0 since it's on the y-axis. So we get r equals y squared. So now the equation of this surface is going to have a form that's inspired by the equation of a circle. We need something squared plus something squared equals r squared. Well, the two things here are the variables that are other than this one. So revolving about the y-axis, these two variables are going to be the other variables, x and z. Now this is going to be the square of the radius. We found the radius to be y squared, so we're going to square y squared. And the equation turns out to be x squared plus z squared equals y to the fourth. So here we're going to find the set of parametric equations, or rather a set of parametric equations for the line that passes through the 2 points P and Q. So in order to find these parametric equations, we need a point on the line. We've got 2 of those, but we also need a direction vector, a vector that indicates the direction of the line. So I think I'll use the vector that goes from the point P to point Q. And so that's going to have components 4, -5, and 1. So one possible answer would be to use, can be arrived at by using, say, point P as our initial point, and then to the 0 we're going to add 4t. From the y we're going to subtract 5t, and to the z we're going to add 1t. So the coefficients of t are just the components of the direction vector. So now we are asked to find the equation of the plane that contains these 3 points P, Q, and R. So in order to find an equation for a plane, what we need is a point on the plane, which we have plenty of, and a vector normal to the plane. So to find this vector normal to the plane, here's what I'm going to do. I'm going to construct 2 vectors in the plane from these 2 points, or rather these 3 points. Now I chose PQ and PR. You could choose any combination of 2 vectors, RQ and QP, for instance. You wouldn't want to do something like pick PR and RP, because that's not really enough information. So, alright, so I'm going to find PQ. So the vector from P to Q has components 4, -5, 1, and the vector from P to R has components 1, negative 2, 0. Now, once we've found these two vectors, we can find a vector orthogonal to both of these vectors and thus normal to the plane by finding the cross product of these two vectors in either order. So I guess I'll find PQ cross PR. So we're going to have I times negative 5 times 0 minus negative 2 times 1 minus j times 4 times 0 minus 1 times 1 and then we're going to have k times negative 8 minus negative 5. So that's going to be, it looks like 2i plus j minus 3k. And so our normal vector would have components 2, 1, and negative 3. So for the equation of our plane, we'll take the x component here, multiply it by x minus that x coordinate, that y component, multiply it by y minus that y coordinate, which will give us y plus 5, and then we'll have minus 3 times z minus that z coordinate, and then that's going to be equal to 0, and that's the equation of the plane, or it's an equation of the plane. Now we're going to find the distance from the point with coordinates 1, 2, 5 to the plane 2x plus y minus z equals 0. So presumably this is a point, this is a plane, and this is a point not on the plane. And this is a formula that I would give you on a test. Alright, so what are we supposed to do? What's this Q? Well, P and one of the points is a point on the plane, and the other is a point off the plane. So this is the point off the plane. We need to find a point on the plane. I'll illustrate this. So we've got this point P off the plane. We need to find another point Q on the plane. And then find this vector from P to Q. So let's find any point on the plane. How about we let x and y be 0 and then figure out what z is. So if x is 0 and y is 0, I believe 0 is, z is also going to have to be 0. So let's let Q be 0, 0, 0. Then the vector from P to Q, or it could be Q to P, either way. Let's go from Q to P. It's not really going to matter for what happens up here since we're going to be taking the absolute value anyway. Alright, so Q to P would be 1, 2, 5. Now what we need to do is take the dot product of this vector with the normal vector. And so that's normal vector is going to have components 2, 1, negative 1. And then we're going to divide that by the magnitude of the normal vector, which would be, let's see, 4 plus 1 plus 1, I think that's square root 6. And we're going to take the absolute value. Again, let me say, if we had found the vector QP instead of PQ, all that would do is change the signs of this vector, and it would change the sign of the thing inside the absolute values. But we're taking the absolute value anyway, so it does not matter. You can go in either order, from the point on the plane, from the point on the plane to the point, from the point off the plane to the point on the plane, or from the point on the plane to the point off the plane when constructing this vector. It does not matter. Alright, so what are we going to get? Looks like we're going to get 2 and 2 minus 5, I think it's negative 1 over root 6, but we're going to take the absolute value, and so that's going to be positive 1 over root 6. for the distance. Here we are going to find the distance between the line with these parametric equations and this point which is not on the line. So what we need to do in order to find this is to find another point, Q, that is on the line. So let's take any value of t. How about t equals 0? If t equals 0, that gives us the point 2, 2, 0, and maybe we can call this point Q. So we've got a point on the line and a point off the line. And then we need the vector from P to Q, or from Q to P, whichever you happen to find is okay. So how about we go from P to Q? So from P to Q, we get the vector 1, 0, minus 5. So that's that vector. Now we need to take the cross product of this vector with the vector u. What is u? U is just a direction vector for the line. And we get the direction vector from the coefficients of t. So those components will be -5, 1, and 3. Let's go ahead and find the magnitude of u. That would be the square root of 25 plus 1 plus 9. I think that's square root 35. Okay, so now we need to find this cross product of PQ here and the vector u. And we're going to be taking the magnitude, so the order doesn't really matter. The order would only change the sign, but we're going to take the magnitude anyway, so it doesn't matter. Alright, so we'll have 1, 0, minus 5, and -5, 1, 3. So we're going to have I times 0 minus a -5. And then minus j times 5 minus 25. 3. 1 times 3, which is 3, minus 5 times 5, which is 25. And then plus k times 1 minus 0. So that's going to be 5i plus 22j plus k. Now we need to find the magnitude of this cross product. So the magnitude of that cross product is going to be the square root of 5 squared, which is 25, plus 22 squared, which I think is 484, plus the magnitude of 1 squared, which is 1. And so this is going to give us square root of 510, I think. So we need to divide this magnitude by the magnitude of the vector u, and we're done. So let's see, 5 will go into 510 102 times, and it'll go into 35 7 times, and I don't think that will reduce. So let's leave it like that.